zeros. So remember that zeros are solutions to the equation. They are where the graph hits the x-axis. That's why they're called zeros, because the y value is equal to 0. And remember that a rational number is an integer. Is a fraction, where it has a number in the numerator and a number in the denominator, usually also just some form of an integer. So the rational zero theorem is if you have a function that has integer coefficients, so not fractions, not square roots, not decimals, has to have integer coefficients, then every rational zero of that function has the following form: p over q. So p would be a factor of the first of the constant, so the last term of the equation, and q would be a factor of the leading coefficient for the function. Let's take a look at a few examples, and these get a little bit lengthy, so remember, anytime you need to, you can pause the video to copy down whatever information you want for your notes, and then pick up when you're ready to move on. Our first example of listing the possible rational zeros would be, we want to list the possible rational zeros of the function using the theorem. And here's our first function. So f of x is equal to x cubed plus 2x squared minus 11x plus 12. So we are focusing on the constant and the leading coefficient. So the constant is 12. So the factors of 12 would be 1, 2, 3, 4, 6, and 12. Of course, we are looking at positive and negatives, because if I have a negative 1 multiplied by a negative 12, it equals a positive 12. Then we want to look at the factors of the leading coefficient. Well, the leading coefficient is 1, so the only factors would be 1 and negative 1. Then we are going to set up the possibilities by taking every single factor of the constant term and putting it over all of the factors of the coefficient. In this case, we just have 1, so it's nice and easy. So that's just our possible rational zeros. We don't know for sure yet if any of these are solutions. We just think they are possibilities. So we've narrowed down from all the vast numbers there are in the world to just these 12 possibilities. And you might be thinking, but Miss Smith, I only see 6 rational numbers. Remember, positive and negative. There's twice as many numbers as you have listed. Okay, so there's the simplified list because we took out the denominator since it was equal to 1. Example 2, f of x is equal to 4x to the 4th minus x cubed minus 3x squared plus 9x minus 10. All right, the factors of the constant term would be positive and negative 1, 2, 5, and 10. And the factors of the leading coefficient are 1, 2, and 4. So set up our possibilities. All of the factors of the constant over 1, all of the factors of the constant over 2, and all of the factors of the constant over 4. So in this case, we have 12 times 2, 24 different possible rational zeros that we would want to go through and test. But at this point, example 1, we're just listing the possibilities. Where necessary, we can go through and simplify. So all of those over 1s can be just simplified to 1, 2, 5, and 10. And then you have 1/2, 1 again, because 2 over 2 is 1, so we've already listed it, we're good there. Then we have 5 over 2. 10 over 2 is 5, that's already listed, so we can take it out. 1 over 4, 2 over 4 is 1/2, that's already listed. 5/4, and then 10/4 is the same thing as 5/2, and we already have that listed. So we're able to take out some duplicates, leaving us with 1, 2, 3, 4, 5, 6, 7, 8 times 2, 16 possible numbers. Went from 24 to 16, so that's pretty nice. All right, so verifying zeros. So remember that we have found zeros of polynomial functions when 1 0 was known. So they gave us in lesson 2.5 one of the zeros or one of the factors. So now we are saying, hey, I don't know any zero whatsoever. Where do I start? So this theorem, this rational zero theorem, gives us that starting point. Let's take a look at an example. So we want to find all of the real zeros of this function, x third minus 8x squared plus 11x plus 20. Step 1, we're going to list all of the possible zeros. So the constant term is 20, so the factors are 1, 2, 4, 5, 10, and 20. And then the coefficient is 1, so the only denominator we have is 1. So we have now listed our possible rational zeros. Positive and negative 1, 2, 4, 5, 10, and 20. Step 2 is that we are going to test these zeros using synthetic substitution or synthetic division. To me, it's the same because it's the same process. All right, so I always like to start off with the positive numbers and start off with the smallest one. So test positive 1. So plug it in. We want to see if our remainder is 0. Since it's not, that means x equaling 1 is not a solution. All right, not a 0. So try negative 1. We plug in negative 1, work through the synthetic division, and look, our remainder is 0. That means negative 1 is a solution. So put that in our list of possibilities. And now we're left with a quadratic function, x squared minus 9x plus 20. So what we do want to try here is to see if we can factor that trinomial. So we've simplified it to this function, having the factors out. Since negative 1 was a solution, that means the factor was x plus 1. And because x squared minus 9x plus 20 is a trinomial that we can factor, we can go ahead and replace that with x minus 4 and x minus 5. Set all of that equal to 0, and then we have our possible solutions. I'm sorry, our not possibles, these are our actual answers. Okay, let's take a look at another example. In example 2, remember that the coefficient was 1. So when the leading coefficient is not 1, the list of possible solutions can increase pretty dramatically. So we want to make sure that, let's go ahead and shorten this by sketching the graph. And when we sketch the graph, we're able to see at least some of these possibilities and narrow down the list. So let's take a look at this function. 10x to the fourth minus 11x x cubed minus 42x squared plus 7x plus 12. Step 1, we're going to list all the possible zeros of the function by putting all of the factors of 12 over all of the factors of 10. And you can see we have quite the list. Step 2 is, let's check for some reasonable values here by graphing the function. And make sure you adjust your window to see all of the twists and turns and the end behavior. Since this was an x to the fourth, that means all of the directions of the graph were pointing in the same direction. And because it was positive, that means they're all pointing up because f of x is going to approach positive infinity. So now when we look at that, we can see that the values negative 3/2, 1/2, 3/5, and 12/5 look pretty close from our list to what we're seeing on the graph. All right, so check those values, and we're going to keep checking until we can come up with a possible solution. So plugging in our first reasonable one based upon our graph, we have negative 3/2, plug it in through synthetic substitution, not a 0. So we plug in 1/2. Plugging it in through synthetic substitution, we see, hey, this is a 0, so that means 1/2 is a solution. Yay! I think there was a typo here because according to the graph and according to this last line, it was supposed to be negative 1/2, not positive 1/2. The textbook has it written correctly, but the PowerPoint did not. All right, so now that we have factored out that binomial, we're left with a new function. So let's take a look at what that new function is. 10x cubed minus 16x squared minus 34x plus 24. Let's go ahead and take a 2 out of there to get it a little bit simpler. 5x to the third power minus 8x squared minus 17x plus 12. All right, multiplying the first factor by 2 to move the 2 basically from the big polynomial to just that linear factor, we're left with 2x plus 1. And you can tell that if you were to set 2x plus 1 equal to 0, it would still be 1/2. So we didn't change the value at all. We're just rearranging this a little bit to make numbers easier to work with. Okay, so now we're going to repeat the steps that we just did for the big trinomial, but now we're using it with the smaller trinomial. And again, your textbook has the equation written correctly. Here are some typos. G of x is equal to 5x cubed minus 8x squared minus 17x plus 12. So any 0 of g would also be a 0 of f. G of x and f of x, we're only using g of x for step 5 because it's we're just looking at part of the function from f of x. So that's the only reason we have it rewritten. Go through the process to list out our rational zeros, so all of the factors of 12 over all of the factors of 5, and then simplify out any repeats. We didn't have any in this case. And we want to show, again, we want to look on the graph. Remember from the previous graph that 3/5 was a possibility. And so let's go ahead and start with that. When we plug it in, which we don't see here because it's a bit repetitious, we see, hey, 3/5 is a solution. So that gives us our second 0. We had 1/5 and negative 1/2. Now we have positive 3/5. And our next function is 5x squared minus 5x minus 20. Again, factor out that 5 and multiply it back into the first term, the first binomial. So we get 5x minus 3 and x squared minus x minus 4. Okay, so using what we know about multiplying functions, if I were to multiply 2x plus 1 times g of x, I would get the same function. So basically, we've just resubstituted some things in that we've taken out. So we have, again, 2x plus 1. That was steps 1, 2, and 3. And now we have 5x minus 3 from steps 4 and 5. And using the quadratic equation, we can solve for any remaining zeros. So here's the quadratic equation, substituting in a, b, and c. When we solve it out, we get that x is equal to 1 plus or minus the square root of 17 over 2. So for our quartic function, we have 4 real zeros. And we could tell from the graph, we saw it hit the graph 4 times. The degree of the function tells you how many possible zeros there are. And when we look at a graph, we can see if all of the zeros are hitting the graph, or hitting the x-axis. So a quartic function would have 4 possible real zeros, and we could tell from looking at the graph that it hit 4 times, so we know that there are 4 real solutions. That gives you a bit of an expectation. If you see a turn where it doesn't hit the x-axis, then we would have some unreal solutions or imaginary solutions. Let's take a look at our word problem. They call it a multi-step problem for this example. Ice sculptures. For some reason, we're freezing a pair of skates. Some ice sculptures are made by filling a mold with water and then freezing it. You're making an ice sculpture for a school dance. It has to be shaped like a pyramid with a height that is 1 foot greater than the length of each side of the square base. The volume of the ice sculpture is 4 cubic feet. What are the dimensions of the mold? So there's our picture, and it's been labeled for us. So step 1, we want to write a verbal equation. So the volume is equal to 1/3 times the area of the base times the height. Again, for a quiz or a test, if you needed any formulas, I would give them to you. Substitute in the numbers, and then simplify out our equation. So 4 equals 1/3 x squared times x plus 1. Multiply each side by 3 so we can simplify, and we get 12 equals x to the third power plus x squared. Subtract 12 from each side, so basically we're setting everything equal to 0. All right, so step 2, now we're going to go through this process of finding these real numbers. So recall from the previous, oops, I don't want to go through that whole thing again, but we need to. Recall that our constant is 12, so we're going to list the factors of 12 over the factors of 1, simplify it out, and we want to test possible solutions. We only want we only want positive solutions because negative values would not make sense. So again, starting with 1, go through synthetic substitution, not a 0. Plug in 2, hey, it is a 0. So we found that 2 is a solution, a possible solution. So we're going to check for other solutions to see if there would be any that could make a satisfactory answer. And unfortunately, because when we plug it in, we get imaginary numbers, that means the only real solution that counted was x equaling 2. So the only reasonable solution is x equals 2. The base of the mold is 2 feet by 2 feet, and the height of the mold is 1 foot greater, so 3 feet. And that is it for our lesson on 2.6. Again, come to class with any questions that you have.